In this video, we are finally going to learn about convolutional operations and the properties of the various parameters that are associated with them. So let's get started.
Convolutions in neural networks. So as I briefly described in the previous videos, convolutions are basically linear operations on two functions. And in our case, these are finite images that we are dealing with and finite filter masks. So everything is discrete in what we're talking about right now. So let's assume that the input to this convolution is an image, and these are usually three-dimensional volumes. So you have the width dimension here, and you have the height dimension, and then you have the depth dimension. So we're going to take this 32 times 32 times 3 input volume, and we're going to convolve this with a 5 by 5 by 3 filter mask. And this filter mask is also called as a kernel, and we can denote it by W. This means that you perform a dot product of weights that are in this kernel with the underlying pixels after you place this kernel at this spatial location, at the input location. And we're going to discuss how this exactly works into more detail in the following slides. What we have to do is to first put this filter mask at this location, and you basically take the dot products of weights in this kernel that you see here with the values of the pixels that are below this in the input in all the channels that are just below the filter mask here. So a filter always extends to the entire depth of the input volume here. Then you perform this operation again by, let's say, that you first have the filter at this location here. Then you perform the convolution. Then you slide the mask again. Then you perform the convolution, and so on and so forth. So what you eventually get is that we get 5 by 5 by 3. So we do 75 dimensional dot product. That's what we will be doing here. We'll be doing a 75 dimensional dot product plus the bias term here. So that's what we denote here in this equation. So you have the weights transpose the input plus the bias term here. Okay, so once you do this dot product, you get an activation here in the activation map. So these are responses that you compute using the dot products, and these are called activations. So basically you get an activation map which is combined of each of these activations, and the activation map here has many activations, and it also goes on row after row in this activation map. So for each of these positions that you would have the kernel over, you would get one activation. Then you would slide the kernel over in the next location, then you would get another activation, and so on and so forth. So how do you decide by how much do you slide this filter? And this is controlled by a parameter that we will talk about in the next slide, but you can either have overlap between these filter locations or no overlap. But here you see there is no overlap, but you can also have an overlap between the locations where you move this filter. And this is controlled by the parameter that we called as a stride, and we will discuss this in the following slides. Here you have the definition of a convolutional operation. And in this slide, we will first contrast it with cross correlation, which is what is actually used in most deep learning libraries that you might use today. So a convolution is defined mathematically as a sum over all m and n in the input image, where you have the index I and j in your image. From that, you subtract the m and the ends, and then the kernel mask k you start from M and N here. And this is an asynchronous way of how you would go through the pixel image and the filter. So in this case, imagine you have an image like this, and then you have a kernel mask like this. So in this image, you would go backward like this. And in the kernel, you would go forward like this. Whereas in cross correlation, which is what is usually implemented in all the packages, it is just a synchronous way of doing that as through going through the image and in the kernel from the top. So for the network, it doesn't really matter because it will learn the weights that needs to bring down the loss either way. So whether you do it in a asynchronous way or a synchronous way, it's the same for the network. So it's just important for debugging for you to know whether you're implementing an extension which is synchronous or which is asynchronous. And in convolutions, the kernel is basically flipped or rotated 180 degrees relative to the input here. And as I said, for the learning algorithm, this basically doesn't really matter, but it's good for you to know because it's mathematically different. Okay, so in this slide again, you see an example of how to use these filter masks and produce the output activations in the case of cross correlation. So in the first example, you take the kernel image and you put it over the image here, and you take the dot product from the kernel with the input. And this would be AW, BX, EY, and FZ. That's what you get here. Then you would move the kernel to the next location here, and then you get BW, CX, FY, GZ. Then again, you would move it to this location. Then you get CW, DX, GY, and HC. That's what you see here. Then in the next row, you would move it in this location, and again here, and so on and so forth. And then you finally get these three outputs here. So basically, you would do the same thing, and you put the filter mask at each of these locations, and you would compute the dot product. So here in this slide, you have a link to a nice animation that you can take a look at. So it shows you how cross correlation basically works even with multiple channels and with padded borders. And we will talk a little bit about padded borders in the following slides. Okay, so now we usually don't just use one convolution in the network. So you learn many filters that gives us many activation maps that you see here. And so you could have one set of weights corresponding to a kernel mask that would produce a response in the first activation map here. And then you have a different set of weights in the kernel that would give you a response in another activation map here. So both of these activation maps would look exactly at the same input patch, but they would be multiplied by the pixels from the input image with their own set of weights. And this would be adapted by the backpropagation algorithm, of course, but you would also initialize them differently. So in a random way, for example. And because of that, the network would learn different filters, and these activation maps are then input to the next convolutional layer and so on. As I said before, all of them look at the same input patch by sliding over the input image, but all of them yield different outputs in their own activation maps that we get here. So for example, let's assume we have an image of 32 times 32 and 3 channels here. So if we had 5 by 5 filters and 6 of them, so we get 6 separate activation maps here. And one thing to note here is that the dimensions of the activation maps are reduced. So here we have 28 by 28, and we'll talk a little bit about that later on. So in each of the weights, you learn different feature detectors. So in the one set of weights in the first activation map, it might look at edges, let's say 45 degrees in orientation. Then in the second filter, in the second activation map, it might look at edges, let's say, for example, 60 degrees orientation, and so on and so forth. So whenever you have an edge in the image at a particular orientation, your filter would then have the highest activation, similar to the experiments that we saw about the visual cortex of cats by Hubert and Wiesel in the previous slides. As we saw, you learn these different activation maps. Now this entire volume of activation map is input to the next convolution. So as we saw in the previous examples, once again, we have an input volume of 32 by 32 times 3, which is then convolved again with a 5 by 5 by 3 filter and 6 of these filters. As always, I said before, the depth of these filters should match the depth of the input volume. Then this yields us 6 feature maps, which are 28 by 28. We again convert these with 5 by 5 filters, 5 by 5 times 6 filters, and 10 of these. And this gives us an output again of 24 by 24, and again 10 of these to match. And we do this again, and we also have ReLU layers in between. One of the things that you should note again is that we start by 32 by 32, and then we go on to 28 by 28, and then we further reduce the feature maps to 24 by 24. And we'll exactly see in the next slides why. All right, so as we said that the network learns these different feature detectors in the activation maps, and these are input to higher layers and so on. So if you look at these feature responses, as we see in the lower features, we notice features such as edges that are oriented differently. And this is very similar once again to the visual cortex of cats experiment by Hubert and Wiesel. And in the mid layer, you have more complex features, which may be colored blobs, let's say corners, for example. And if we go to higher layers, features that they form are really complex representations, which are basically combinations of these mid and low level features. So this is once again very similar to the Hubert and Wiesel experiment. And this was never actually hand trained. So these features that you see here are learned by the networks themselves. So a very important effect of using these convolutional operations than rather fully connected networks or the multi-layer perceptrons that you learned earlier in the beginning is the huge reduction in weights, because you only use the local connected filters by doing these convolutions, and we have a massive amount of saving in parameters. So if you take this example here, you have a 200 by 200 grayscale image. So if you have fully connected neural networks, about 400,000 hidden units, then approximately it would consume 16 times 10 to the power 9 parameters here. Whereas if you only have local connectivity, and if you have the same number of 400,000 hidden units, which let's say 10 by 10 fields, then you get only about 40 million parameters here. And this is a significant amount of reduction, and this is primarily caused by causes a regularization effect. So it reuses the parameters at each of these locations when you slide the kernel over. And this is why we get a reduction in parameters when we use convolutions. Okay, backprop through convolutions. Let's assume we have an input vector xi and we have an output vector wi. And to produce the output, we compute a weighted sum of our window and we multiply them by the weights wj. So how can we backpropagate through this? So since this is a linear module, to backpropagate through a linear module, we can write this formula that we see here. So the gradient of some cost with respect to xj is equal to sum over k, which is the index running over the weights of the gradient of the same cost with respect to the output for j minus k. So a particular x here will send its output to y's that are towards the left of it because of the convolutional formula basically here. So you take the y's that are on the left of the x's, and well above you compute the weighted sum of the gradients backwards, and you get the gradients with respect to the input. And that's this formula that you see here. So we also need to backprop with respect to the weight wj. So we have one input x here and an output y and a weight that connects these two. So we have seen that for a linear module, we take the gradient with respect to the output multiplied by the input, and that gives the gradient with respect to the weight. So that is the partial of the cost with respect to the partial of wi multiplied by x of I plus j. But the problem is that in convolutions, the weight wj is shared across all the dimensions in the convolution. So we have to sum up the gradients with respect to each of the individual instances of this weight wj to get the overall gradient. So that's this formula in the bottom that is shown here. So the gradient of some cost with respect to wj is equal to the sum of the locations in the vector of the gradient of this cost by partial of yi multiplied by x of I plus j. So is what the weight basically connects here. So you will learn more about this in the exercises, but basically all the deep learning libraries that you use actually automatically do this for you. Okay, so let's look at how the convolutions will change the spatial dimensions. So we saw already before that as we implemented these convolutions from stage to stage, the actual dimensions of the output got smaller. Now we will see why that is the case. Let's assume we have a 7 by 7 input and a 3 by 3 filter. So if we slide this filter over the image and we compute the first output activation map, combining all these pixel values under this filter mask with basically the weights over the filter masks that we get here, then once again we would slide this one pixel over, and as you see here, compute the feature responses at this location. So again, you would keep doing this, and in the end, because we moved 5 times, you get a 5 by 5 output here. And because we would also keep moving them like this, basically again and again, then in the next row here, that's what gives us this 5 by 5 output. Now, if we change the parameter that controls by how much we slide this filter mask, this parameter is called as the stride. So in this example that we saw before, we slide the feature mask after every pixel. And now if we slide it by 2 pixels, that is with a stride of 2, and we do the same thing again, we move it by 2, then we see that we get an output of 3 by 3 using a stride of 2. So basically with a stride of 2, we get an output of 3 by 3. So a general formula for this is that if we have an input of size n by n, and we have a filter of size f by f, and the stride S, then the output size can be given by n minus f divided by stride plus 1. As we saw in the first example, if we had a stride of 1, so we then got an output of 5 by 5. Then we had a stride of 2, so then we got an output of 3 by 3. Now what happens when you have a stride of 3? So as you can see here, this really doesn't work out. We don't do convolutions like this because this is going to give us asymptomatic outputs. Okay, so in some cases, you don't want the dimensions to change between these convolutional operations, and you don't want to lose the resolution. So what you can do is that you can zero pad around the image as you see here. And here you see that the white parts of the original image and the gray parts are the zero pads that are filled with zeros. So we start again at the top left, including the zero padding borders around the image. And if we do that, we get 7 by 7 output. So it's quite common to use in practice, and depending on the filter size, you will use different zero paddings. So if you have a filter size of 3, then you would want to zero pad with 1. And if you have a filter size of 5, then you would want to zero pad with 2. And if you have a filter size of 7, then you will want to zero pad with 3, and so on. So if you have no padding, then the kernel is required to be fully contained inside the image. Then we call this a valid convolution. And if you have padding, and if you want to keep the size of the image constant throughout successful convolutions, then we call this as a same convolution. So here you see a summary of convolutional layer that you can read a little bit more in detail carefully. So if you have an input volume of W times H times D, and you have parameters for the convolutions, which are basically K number of filters, filters having spatial extent F, a stride S, and the amount of zero padding as P. With this formula that is basically shown here, you can compute the output volume size of the convolution. And here you can also compute the number of parameters that your convolution is going to have. All right, so that brings us to the end of this video. I have 2 questions for you. Let's assume we have an input volume of 32 times 32 times 3, and we have 5 by 5 filters of 10 of them with stride 1 and padding 2. Now, what is the output volume size? And how many parameters are there in this layer? So with the formulas that we saw in the previous slide, you can compute these values. So I encourage you to pause this video now and to try to compute these values. We will continue in the next video. Thank you.